Welcome back, folks. In our last video, we learned how to calculate volumes of solids of revolution using the method of cylindrical shells. While we've seen a couple simple examples, the purpose of this video is to explore some variations. Throughout the video, we're going to be studying this region R, which is enclosed between the graphs of y equals root x and y equals x over 3 from x equals 0 to x equals 9. In each part of the problem, we're going to set up the integral for the volume of the solid that we would obtain by revolving R about some axis, but we won't worry about actually evaluating the integral here. You can do it for practice if you want. Before we jump into part A, I will just mention that you already have all the necessary knowledge to tackle these problems yourself, so I suggest pausing and trying each one before you see me solve it. That's how you become really good at these problems. Okay, in part A, we're revolving the region about the y-axis. I've sketched the region here, which is how you should start any volume problem. And you can see that those bounds of 0 and 9, they're exactly the points where the curves intersect, right? You could plug 9 into each one and you would see that the y value at each of these curves is the same. It's 3. To set up the integral, I have to imagine the region rotating into the screen and emerging over here, mirrored on the left-hand side. I'm going to have cylindrical shells at each x value between 0 and 9. Here's one of them. The volume of the solid is then the integral from 0 to 9 of a of x dx, where a of x is the area of the shell. It's 2 pi rh. Here r is the radius and h is the height. You can see from the picture that the shell has radius x. For the height, it's actually the difference in the heights of these two curves, right? Upper minus lower. We therefore have h equals root x minus x over 3. Aha, so it seems that the volume is going to be the integral from 0 to 9 of 2 pi rh, so it's 2 pi x times the square root of x minus x over 3 dx. There you have it. Let's try some more. Okay, in part B, we're working with the same region as in A, but this time we're rotating it about a different axis, the vertical line x equals minus 4. I've drawn that line over here to the left of the y-axis. Again, pause the video and try it yourself before you watch the full solution to this problem. Just as before, I'm going to start by drawing the mirror image of my region when it pops out of the screen on the other side of the axis. Maybe it looks something like this. I'm also going to draw in one cylindrical shell, which starts as a strip at some x between 0 and 9, maybe this one here. And I'm going to remember that the volume is the integral between 0 and 9 of the area of that shell times dx. Since area is 2 pi rh, we need to figure out the radius and height of the shell. Well, folks, the height of the shell, I believe, is the same as in A, right? It's the difference in the heights of these two curves, root x minus x over 3. For the radius, note that to get from the axis of rotation all the way to the edge of the shell over here, we would first need to travel 4 units just to get back to the y-axis, and then we'd need to travel x more units to get to the edge of the shell. So the total distance, 4 plus x, that's going to be our radius. Putting everything together, the volume of my solid is the integral of 2 pi rh, where r is 4 plus x, and h is square root x minus x over 3. In part C, we're rotating about the vertical axis x equals 12. This time, the axis is to the right of our region, but the process is still the same. Give it a try. When the region pops out of the screen, it might look something like this. Also, here's what a typical cylindrical shell would look like, drawn at some x between 0 and 9. As usual, the question is, what's the radius and what's the height? The height is the same as in A and B, right? H equals square root x minus x over 3. The radius, though, might be a little bit trickier. You have to notice that this full distance between the y-axis and the axis of rotation is 12 units, right? And this smaller distance here from the y-axis to the edge of the shell is x units. Since we want just this chunk here from x to 12, we would need to subtract. The radius is the full 12 units minus this little length here of x units. R in this case would be 12 minus x. From here, you know the drill. The volume is the integral from 0 to 9 of a of x dx. A of x is 2 pi rh. Using the r and h we found above, I'm getting the integral of 2 pi times 12 minus x times the square root of x minus x over 3 dx. Alrighty, last one, my friends, and this one's a bit different. While all of our earlier examples have been rotating about vertical axes, this time we're rotating our region about the x-axis. Can we still use cylindrical shells to solve this problem? Yes, we can. We again draw out our region as it appears after it's rotated about the axis, and we draw out a typical cylindrical shell. Since the shells are always centered about the axis of rotation, this time our shells are going to be tipped on their side, opening in the direction of the x-axis. Ah, cool. The shells this time don't start as vertical strips at some x value like before. Now they start as horizontal strips at some y value, some y between 0 and this point over here, which I think we found earlier was 3. The thickness of the shell is not dx like it was previously, it's dy. And therefore, we're going to have to integrate with respect to y if we want to use the shell method here. At this point, folks, the process is the same. We integrate a of y dy, where a of y is 2 pi rh, the area of the shell. The radius r appears to be given by this distance here, which is y, so r is y, while the height of the shell, which is really over here, right, since the shell is tipped on its side, is given by this horizontal distance, the x value for the line, minus this horizontal distance, the x value for the root function. If we solve for those x's, from the line we get x equals 3y, and from the root function we get x equals y squared. Therefore, the height h is right minus left. It would be 3y minus y squared. Thus, the volume of our solid is given by the integral from y equals 0 to y equals 3 of 2 pi rh, where r is y and h is 3y minus y squared. Now, folks, was this really the easiest approach for solving this problem? No way. It would have been way easier to actually use disks and washers because that would allow us to stick with functions of x. Indeed, if you imagine slicing the solid along the x-axis, from x equals 0 to x equals 9, you would get washers that look something like this. The volume of the solid is given by the integral of the area of the washer times dx from x equals 0 to 9, and we know that the area of the washer is pi times the outer radius squared minus pi times the inner radius squared. From our picture, the outer radius of the washer is root x, it's given by the root function there, and the inner radius is given by x over 3, it's given by the line. So there you have it, folks. This would be our volume integral if we set it up using washers. Much quicker, right? Because we didn't have to worry about expressing things in terms of y. Let's now wrap up this video with a couple pointers on when to use shells versus when to use disks or washers. The choice to use shells versus disks or washers will ultimately come down to two factors. First, the type of axis around which you're rotating, and second, whether you would prefer to work with functions of x or functions of y. As we saw in the last example, if you're rotating about a horizontal axis and wish to work with functions of x, the disk/washer method will be the better approach. You may still be able to solve your problem using cylindrical shells, but this would require setting up an integral with respect to y. If that seems like it would be a pain, don't use that method. With vertical axes, on the other hand, we have the opposite situation. If you want to stick with functions of x, we've seen in many examples throughout this video that the shell method is the way to go. However, if you would really prefer to use disks or washers, that may be possible too. You would just need to express everything in terms of y.